All right, in this explainer, we're diving into a question that gets to the very heart of reality itself. It's something you'd think physics figured out ages ago, but maybe not.
So what is the universe really made of? I mean, what are the fundamental building blocks of everything you see around you? Of you?
For hundreds of years, the answer felt so simple, so intuitive. Going all the way back to Isaac Newton, we pictured the universe as being built from these impossibly tiny points, kind of like little solid dots zipping through space, and we call them particles.
And this idea, the point particle, it's been incredibly sticky. It has hung around right into the heart of modern science, shaping pretty much how we think about everything. But what if that cornerstone, that fundamental idea that's guided physics for so long, is just plain wrong? What if we've been looking at reality through the completely wrong lens this entire time?
So the first big crack in this whole particle picture came from the super weird world of quantum mechanics. And it all kicks off with one single equation that basically changed the game forever.
Every single quantum theory, when you get right down to it, starts with the Schrödinger equation. Its job, or so we thought, was to describe the behavior of one little quantum particle, like a quantum version of Newton's tiny billiard ball.
But here is the massive twist, the thing that has had physicists scratching their heads for a century. The answers you get from the equation, what it's actually describing, they aren't points, not at all. They're waves, things that are spread out across space.
So if the equation isn't describing a particle, then what is it describing? Well, a field. And a field sounds really technical, but the concept is actually simple. It's just something that has a value at every single point in space. Think about the temperature in a room. That's a field.
But the idea of a point particle was so baked into our thinking that scientists didn't just accept this new wave description. Nope. Instead, they came up with some incredibly clever and honestly incredibly complicated fixes to try and force that old particle idea into this new way of reality.
You can basically boil it down to two big attempts. On the left, you have the probability wave idea. This says the wave is just a cloud of possibilities that, poof, collapses down to a single point, our particle, the very moment we look at it. On the right is the quantum field approach. This one says, let's treat the entire field as a quantum thing, and particles are just specific little spikes of energy within that field. The key thing here is that both of these are just complicated ways to shoehorn a particle into a theory that is screaming waves.
But see, trying to force this particle idea on the math, it leads to some really, really weird consequences. These patches end up creating more problems than they actually solve.
And this leads to one of the most bizarre problems of all. If you take that probability wave idea seriously, you run into this wild dimension issue. To describe one particle, okay, you need our normal 3 dimensions of space. But to describe 2 connected particles, the math suddenly needs a 6-dimensional space. 3 particles, now you need 9 dimensions, and it keeps going up. Does that really sound like our reality?
Okay, so things got complicated really fast. But what if there's a simpler, way more elegant way to look at all this? This is what leads us to a pretty profound revelation about what the universe is really like.
So, what if we just stop? What if we stop trying to cram our very human idea of a particle onto the mathematics?
What if the Schrödinger equation wasn't some confusing puzzle we had to solve, but was just telling us the plain truth about reality all along?
If we do that, if we just listen to what the math has been screaming at us for 100 years, we come to a pretty startling conclusion. Reality is not made of particles.
It's made of fields. The universe isn't a collection of tiny separate dots, it's a tapestry of continuous, flowing fields that fill up all of space.
Now, I know this might sound like some fringe idea, but it's not just a philosophical preference. The proof for this field-based reality is hiding in plain sight, right inside the most successful theory of physics we have ever come up with.
The logic here is surprisingly direct. Step 1. Our best theory, the Standard Model, is built on equations that describe waves moving close to the speed of light. Step 2. These are, at their very core, field equations. Step 3. Remember that Schrödinger equation we talked about? It's really just a simplified slow-motion version of these bigger field equations, which leads us straight to Step 4. Our most successful theory of reality is fundamentally a field theory.
And the implication of that is just mind-blowing. It suggests that a classical field theory, a theory of continuous, smooth fields, is actually more fundamental than quantum mechanics.
From this point of view, all the weirdness of quantum mechanics just emerges from the complex behavior of these underlying fields.
And hey, don't just take my word for it. As the source material says directly, the Standard Model is exactly that, a classical field theory. It's not a theory of particles, it's a theory of fields that we just happen to have named the Standard Model of particle physics.
So, the huge takeaway here is this. The particle was never really there. It's a useful illusion. What we detect in experiments and call a particle is really just a concentrated ripple in an underlying field. It's like pointing at the crest of a wave in the ocean and insisting it's a separate, solid object.
And that brings us to the final thought. If the particle, the most basic building block we imagined for centuries, is just an invention, a convenient story we told ourselves to make sense of the math, it really makes you wonder what else in our understanding of reality is too.